we talked about trees, we talked about commits, and we mentioned annotated tags. And last time we saw blobs and we saw trees. And if you remember, we said that blobs correspond to files and trees correspond to directories. So whenever you check a directory into GIT, you should expect to see a corresponding tree object. Whenever you add a file to GIT, that file will be stored in a blob. We actually went through the process of adding a file to GIT to see that we could find the blob and we could find a corresponding tree. You still remember that? Did that make sense to you? That whenever you store files and directories in GIT, you get these objects that represent them. Now, there were two things that we did not have time to cover last time. And I think they're mentioned on the problem set, so we'll have to go through them real quickly. And so let me see if I can bring up the slides. And let me then try and find the right slide. The object store, we talked about that. And we mentioned the index as the staging area. We'll come back to that. Right, it should be part of this set of slides. We talked about adding blobs using git add. You can use git cat file to inspect the blobs. Now let me see here. We should have some, yes, there we go. Pack files. I did not get to talk about those last time. So we mentioned that when you add a file to Git, you get a blob object that corresponds to that file. That file gets stored in a blob. However, you of course check a lot of files into Git. In a large project, you'll check, you might have literally thousands of commits. And if every time you create a commit that contains a given file, naively you might expect that you'd actually end up with thousands of copies of what is essentially the same file. Of course, that would be really inefficient, and that's not how Git does things. What ends up happening is that Git will compare files in your repository. And whenever it finds two blobs that are really similar to each other, what Git will do is to just extract information about how you get from one to another. Say by adding a line, deleting a line, modifying a line in a certain way. And that's the information that gets stored. There's a process that happens in the background pretty regularly. You won't see it, which will go through the objects that you've checked in, or the blobs that you've checked in, and it'll pack them together into a pack file. So that's not something you'll see in everyday life, but you can actually get Git to do it. You can manually start that process by running what's called the garbage collection. In Git, that's done by running the command git gc. It runs every so often and you won't even see it because it happens in the background, but you can trigger it. So let's have a quick look at what that means. Let me bring up the terminal. And let me get three. Let me create the directory. And just follow along on screen. You don't have to do this on your own computers. I just want to show you what this looks like. So I'm initializing a new repository. And I'm creating a file. Let's just do the boring thing. Hello, Umuzi. We'll call that Umuzi.txt. Now we have a file called Umuzi.txt. And if I do git add on that file, it will be added to the object store. If I check the hash of that file, I find that the hash that corresponds to that object is 00f2, etc. And now, just to make sure that I can find it again, I'll do git catfile -p and the hash, and there you go. It exists, and the content is hello Umuzi, as we expect. This is what we did last time. We did exactly this. We also looked at, we also located the object itself inside the .git folder. So now we're inside .git, and there's an object catalog, an objects directory, and inside here there's a directory that starts with 00, which are the first two characters of that object's hash. And inside that directory we find F2, etc., which are the next two characters and the rest of the hash. So Git stores the objects by chopping off the first two characters. That will be the name of the directory, and the rest of the hash will be the name of the file. It's just a way of making sure you don't get too many blobs inside a single directory. So there we go. We actually located the file that contains that blob. Let's now go back and create a very similar file. We have Umuzi.txt. Let's changing by adding hello Umuzi, glad to see you. Now, what we did now is just to modify the file. We added a line, glad to see you. And if we now add that object to git add Umuzi.txt, now we've added another blob to the object store. And that object has a different hash, of course, because it's a different file, it's a different blob, it gets a different hash, B319. Let's go and find that file inside the object store, git objects. Okay, now there's a directory called B3, which are the first two characters of that object's hash. And 19, etc. 19D4. That's the rest of the hash. And here we go. That's the actual file that corresponds to that blob. Okay. But now we said that garbage collection will actually probably reduce these two blobs to a base blob and a delta. A piece of data that says how you get from one to the other. So if you now run git gc, git garbage collect. Garbage collect says enumerating objects 1 done, etc., etc. If we now enter the directory .git objects, we should find that the directories are gone. 00 is left. The original one is left. I'm guessing. That one's still there. Now we also have a pack file, which is sort of a cryptically named file, but it contains information about all the other files that have been packed together. So now we reduced two blobs to a blob and a file that says something about the difference between the next blob and the original blob. So that's pack files and garbage collection. Now, I think we mentioned the index last time. Do you remember that? Do you remember what the index is? If you do, just say something about what the index is. We mentioned index as the other main primary data structure next to the object store that is vital to how Git functions. You remember what the index is used for? Are you able to sum that up into a simple description? Let me bring the slides back up. We did briefly look at the index last time, didn't we? And if you don't remember anything, just say so. If we covered it too fast last time, just say so. Are you still there? I'm not getting any feedback from any of you. Or is the chat still working? The index. Okay, you don't remember. Right. So the index, that's actually the list of files in your working directory that you've told Git, I want to keep these files when I commit. So whenever you change a file in your working directory and you run git add on it, it goes into the index. It's basically the list of files in your working directory that Git knows about. And whenever you commit, those will be the files inside your commit. Those will be the files or the blobs that will be brought into your commit. So you're saying it was covered too fast. It probably was. Okay, so let me see if I can show you an example of this. Let me switch back to the terminal. And we're in this directory now. We have a file called Umuzi.txt. I haven't created any commits. We haven't even talked about what a commit is, but we will. And you probably use Git to create commits already, so I presume that you have some intuition of what a commit is. Oh, did the terminal switch again? Why does it do that sometimes? Okay, hopefully you can see the terminal now. But what I've done is I've added Umuzi.txt by running git add. And that means that it'll be tracked by Git. It goes into the list of files which Git knows about in my working directory. And we can query the index to see what kind of, we can see all the files that are in the index by running git ls files stage. Because remember, another name for the index is the staging area. And it'll tell us that the only file it knows about right now is Umuzi.txt, which corresponds to a blob with the hash B319, which is the object we just added. If I create a commit right now, those will be the files added to that commit. Those will be the files that are checked in. Now, if I just simply make another change to the file, Umuzi.txt, this is line 3. Okay, I just added another line. What now? Has anything happened that Git knows about? No. I've made a change, but I haven't made Git aware of the change. And the only way of knowing what Git knows about is by checking the index. Git ls files still shows us that it thinks that Umuzi.txt should be the blob with hash B319, which is a different file. In order to make Git aware of the changes, I have to add the file to the index by running git add Umuzi.txt. Now, if I check the staging area, if I check the index again, we can see that, all right, Git has changed something. It's changed the blob that corresponds to Umuzi.txt. So exactly, Singy, we did not add it to Git. If we don't run git add, nothing happens. Git won't magically say, I think that these changes that you made, they should be added to Git. No, you have to explicitly add them by telling the index that, hey, I changed a file, add this file to the index. Does that make sense? Hopefully it does. Now, of course, checking the staging area would be a bit cumbersome if we had to run git ls files -- stage all the time, which is a really long and horrible command to have to type out. So that's not usually what that's not how we're supposed to check the index. What we're supposed to do is to run git status, which will tell us about files that have changed since the last index. And now it's telling us that so far it knows about Umuzi.txt. We've added it. It says that that's going to be a new file if we make a commit, but Git knows about it. That's why it's shown in green. And it's listed under changes to be committed. If I now make another change to Umuzi.txt, say by deleting this line, we've now made a change. Umuzi.txt in our working directory is now different from the Umuzi.txt in our index. If we now run git status, Git will tell us that, hey, there's a change here. We already know that there's a file called Umuzi.txt that will be created, but in your working directory, you've actually modified that file. So the file in your working directory, Umuzi.txt, is different from the Umuzi.txt that the index knows about. And that's why it's shown in red as changes not staged for commit. Remember, the index is also called the staging area. If a change is not staged, it hasn't been added to the index. So git status is usually how you'll check if your working directory and the index are in sync. And I think git status is probably a command that you've used already. Those of you who have used Git, I think that's most of you. You've run git status, I guess. Have you? Is it a command you know about? So what's important here is to know that what we're comparing our working directory against is the index. And git status will show you the difference between the index and your current working directory. That's the main takeaway here. Okay, and it looks like Michelle is here. Great to see you. So I think we won't say any more about the index. We'll encounter it again, but just think about it as the list of changes, the list of files that Git knows about in your working directory. And when you commit, the commit will be created from the index. Now we use the word commit so many times. I think it's about time we actually go and talk about what a commit is. We have a question. If you add a file before you commit and then modify it and you don't add it, which one will be committed? So yeah, if you add a file, a blob will be created for that file, which contains the literal content of that file. And that will be put into the staging area. If you then modify the file in your working directory and you don't add it, then Git won't know about the changes you made. Git will not make any modifications. If you then actually commit, the first file you added is the one that's going to be committed. And the changes that you made to it will not be committed. Was that clear? So basically, when you run git add, you're making a snapshot of that file and you're telling Git, you know, put this into the index. This is a file that will be committed. If you don't do that, your changes will not be recorded. So we've talked about commits now, and commits are yet another kind of object that we find in the object store. And the commits can basically be thought of as a snapshot of the working directory, or better yet, maybe we should say the files that you've added to the index, right? The files that you've made Git aware of and that you've checked in. So basically a commit is created from the index, from the changes from the files that you've made Git aware of. When you run git commit, a commit object is created, which sort of freezes that content, that index in place with some more information. That's a commit. A commit contains the following data. It contains a tree. Remember, a tree represents a directory. It represents the top level directory of, the working directory. And a tree again refers to blobs, which are the files that exist inside that directory. Then a commit contains an author name, an author email, the committer's name and the committer's email, because those two could be different. Say, I could write a piece of code and not check it in, and then Michelle or Peter could check it in or commit it for me. In that case, you could actually set the author name and the committer name to be different. Then you get the timestamp that says the date and time when the commit happened, a commit message, and importantly, a commit says what its parents are, or is if it's a single parent. And there's only a single commit in Git that doesn't have a parent. That's the first commit you add. Every other commit inside your Git repository will have at least one parent. Optionally, it's also possible to add a digital signature if to a commit to verify cryptographically that the commit is yours, but that's not a topic that we'll cover. That's optional, so forget about it and look into it on your own if you're interested. What's important is it contains a tree, that is a snapshot of your working directory. It contains author, name, and committer name and email, a time, and a commit message, and information about parents. Now, a commit is also an object, so of course a commit has a hash, and it's referred to by its hash. The hash of a commit is actually literally the hash of all the information that we just mentioned. There's a file inside Git that contains literally the text tree and then its hash, an author hash, author and the author's name, author email and the author's email, etc. It takes that file content and it hashes it, and that becomes the name of that commit, the hash of that commit. And in all of Git, hashes is what we're using to refer to commits. A commit is named by its hash. It's identified by its hash. So here's an example of listing. We're using git log, the output of a Git repository, and you can see it starts with commit and then its hash. And then you can see the author's name, the date it was committed, and the commit message. All the other information is still there, but it's not shown when you do git log. This is a printout from the actual repository I used for these slides that you're looking at right now. So yeah, every commit has a hash that identifies it, as you can see up top in yellow. And then you see all this other information as well. So a commit can be diagrammed as you see here. It points to a tree. It has a tree, And the tree says something about the blobs, i.e. the files that have been frozen into place in this commit, and author, committer, etc., etc. So whenever you check something into Git, whenever you create a commit, all these objects will be created in the object store. Blob objects that correspond to the given files, tree objects that correspond to the directories, and a commit object which represents the code that you've checked in. Now, the great thing about commits, and all we've talked about so far, is that since a commit refers to a tree by its hash, and a tree refers to files by their hashes, if any change happens to a file inside a tree, the hash of that tree will be wildly different. If any change at all happens to a file or a blob, the hash of that blob will be wildly different. So if any change at all happens to the files that are checked in, that will be reflected inside the commit by a very, very different hash. However, if a commit has the same tree hash as another commit, you can be certain that those are the exact same files and the exact same working directory. Also, since a commit contains the parent's hash, if anything is changed about the parents of a commit, the hash changes completely. So in other words, if you look at the commit's hash, that completely identifies all the information that was hashed. So in order for Git to compare two commits, all it does is to look at its hash. All it has to do is to compare 40 characters, which is amazing. It's a really fast way of comparing commits and comparing really a lot of data. So say I have a commit in my Git repository and I want to check, hey, Michelle, Peter, do you have the exact same files and the exact same commit as I do? That could be a huge repository with gigabytes and gigabytes of files. All I need to do to verify that Michelle or Peter have the exact same data as I do with the exact same commit is by just verifying that, oh yeah, your commit has hash A, B, C, D, E, F, etc. Mine has hash A, B, C, D, E, F as well. The hashes are identical. Therefore, we know that the files are identical, the history is identical, the committer's name is identical, the author's name is identical, everything's identical. That's all really by probability, because remember, a hash just says that it's very, very likely for something to not have changed. If two files have the same hash, we're saying it's very, very likely that they are the same. It's exceedingly likely. The probability of two files being different and having the same hash is so small that we can basically rule it out. So it works by the laws of probability, but we can be so certain about it that there's a greater chance that your computer malfunctions by chance and prints out a wrong result due to cosmic rays or something outside the realm of what ought to happen than two commits to have the same hash just based by probability alone. So yeah, that's how Git can make comparisons so quickly. Just check commits. Now, as we've said, creating a commit happens using the index. You use git add to add files to the index. When you run git commit, Git creates a commit by constructing the necessary trees from the index and making sure that it has all the necessary blobs. And when you then run git commit, the parent of the commit that you've created will of course be the previously checked out commit. Now there's another way of creating a commit as well, and that's by merging other commits. If you run git merge, you take the content of two commits, you compare the content, and sometimes you have to select what content to keep from which of the commits, and it'll create a completely new commit based on the two others. And in that case, you get a commit with more than one parent. And as we've seen already, if you actually draw commits out and you connect children and parents with edges, we get a commit graph. We get a DAG, like the one we looked at earlier. And if you want to actually look at the commit graph, you can run git log -- graph, and it'll show you the log with lines between the different commits. And it'll look as this. So this is an example from a project at work where, as you can see, commits have been branched off of each other and then merged back in. And we'll look at exactly why this graph looks like this later on, but you can at least, I hope, recognize this as a graph. And you can see that the commits fit together by lines that connect ancestors and identify which commit led to the next. We're going to run a practical example of how this works in a minute. So if this is a lot of information to take in, we'll actually make this a bit more concrete. Actually, I think we'll do that now. If all of you could just bring up your terminals, we're going to run a small session on how commits work. So I'll give you a minute to get your computers ready. Just tell me when you are ready. Create a new directory and initialize git. And tell me when you're ready. Okay, and tell me when you have a git repository initialized and ready to use. Okay, very good. Oh, and again. There. Okay, now add a file to first the working directory and then the index. So I'm going to create a very simple file. Roses are red, violets are blue. Poem.txt. Okay, just create a file with any content at all. It doesn't have to be what I typed just now. Roses are red, violets are blue. It doesn't have to be that. Just create a simple text file with whatever content you want. And tell me when you're ready. Remember, an easy way of doing that is by running echo, writing something, and piping it to a file. Okay, very good. Now we've created this file, but Git doesn't know about it yet. If you run git status, you'll see that poem.txt is an untracked file, meaning that it exists, but the index doesn't know about it. Therefore, Git doesn't know about it. So if you run git status, you should find that the file is untracked. Is that correct? And when you've verified that the file is untracked, add it to Git by running git add poem.txt. And now if you run git status, it's listed as changes to be committed. Is that correct? That means we've added the file to the index. So Git knows about this file now, and when we create a commit, that file is going to be inserted into that commit. That file is going to be among the blobs inside the tree referred to by the commit. Now we're going to create a commit. And we're going to run git commit. And we're going to just add the commit message directly here by using -m. Add text file. That's going to be my comment. This is going to create a commit object. And it tells you that on the branch master, and branches will be our next topic, it created a commit whose hash starts with, in my case, 7th C3FF. In your case, that might be different. Tell me when all of you have created this commit now. Just give me a heads up whenever you've run git commit. -m will just allow you to type the commit message right there and then. And you're done. Okay, very good. Now what we can do is to run git log to get the commit log. Git log will show you the latest commits, and you should find that it's added as a commit with hash, in my case, 7C3FF, etc. The author should be your name. The author email should be your email. The date should be the current date and time. And you should find the commit message. Yeah? Now, remember we talked about the object store. It contains blobs and trees and commits and tags. Yeah, we can query the object store directly to find our commit again, and we're going to do that now. Remember git cat file, which we used to inspect blobs and trees. Let's run it now to inspect this commit, and we're running git cat file -p and then the commit hash. Do that and you will find the actual raw content of this commit. And you'll find that the commit has a tree, it has an author, which is me, and a committer. And after the author line, you'll find the timestamp of when it was created and when it was committed. So tell me if you've been able to do that. We actually looked inside, we peered inside Git's object store. We looked at the Git internals. We opened the hood to look at the engine. And we printed out the raw information inside that commit to see what it looks like if you take the casing off. And that's what it looks like. You can see the tree, you can see the author, you can see the committer, and you can see the commit message. And the hash of that commit is literally the SHA-1 hash of that information. Now what we will do is to again inspect the tree. Run git cat file -p to print it on the tree hash. And you should find that that tree represents a directory which contains a single file, namely poem.txt. In my case, it's called poem.txt. You might have called it something different. And lastly, if we now have a look at that blob by running git cat file-p and the name of that blob, i.e. its hash. You should recover the content of that file. Roses are red, violets are blue. Well, that's what I wrote. Okay, we started a bit late. We started at 18 minutes past, so we'll go on for a few more minutes. I hope that's okay. Because what I want us to do now is to open that file that we just created and modify it. But before we do that, is everyone ready? Did everyone get to this stage where you were able to recover the hash of your blob and print it? So remember what we did. We created a commit, then we actually looked inside that commit to find its tree and all the other information that is associated with a commit. Then we inspected the tree, and inside that tree we found a blob, and that blob of course corresponds to a file in real life. When we inspected the blob, we were able to recover the content of the file that we had checked into Git. Okay, very good. And I'll just wait for Michelle or Peter to verify that most people or everyone is ready. So I'll give you a few minutes or as much time as you need. Now, of course, if we look at the commit graph, it's a very simple commit graph now. We created one commit, so our commit graph is just one node. Git log graph. That star, that asterisk, corresponds to the only node we have in our commit graph, which is the initial commit. Okay, Michelle is heading out. That's fine. You'll just tell me if you're ready or not, and if you're not ready, whenever I ask you, just say, oh no, wait, okay? And that's completely fine. Now what we'll do is to modify the file. So you can do that in a text editor of your choice. You can do it on the command line if you want to. Just add to it or modify it in any way you want. Violets are blue. Sugar is sweet. And so are you. Okay, I just completed the poem. And run git status. And you'll find that Git doesn't know about this file yet. Git can see that it's been changed, but we haven't added the changes to the index yet. We haven't added the file to the index. So again, you'll have to run git add poem.txt. Well, that's what my file is called. Now it's added to the index. And when you've done that, commit again. With some new commit message. And tell me when you're ready. So we now created a second commit. And according to my output, that commit has hash 63672. Your commit will be different because your names are different, your emails are different, the time you commit is different, the blobs are probably different as well. So just give me a heads up when you've been able to modify the file and you're ready. So you should have modified the file, you should have added it to the index and created a commit. So at least one of you is done. What about the rest of you? Done. Okay. Very good. What about the rest of you? And just, make sure to help each other if anyone's stuck or if anything is taking time for technical reasons. Go around and assist each other. Make sure that you get to the point where all this is done. Check with your neighbor. Okay, is everyone done? If not, just say so. Just tell me. Give me another minute. So, if one of you could verify if everyone's ready and tell me that everyone's ready, I'd appreciate it. So, where are we at? So hopefully most of you know how to modify files. There's a problem, well, at least one problem on the problem set, which is about modifying files. You can either do it in a text editor of your choice, or you could, either you can do it in a graphical text editor, or you can do it on the terminal. So it seems like everyone's ready. Very good. Thank you, Peter. Thank you very much. Now, what I want you to do is, again, run git log and find the commit. You should see this. You should see it listed as the first commit in git log, correct? Now, of course, what git log does not do is to show you the actual commit graph, which is why you should add --graph to git log to see that one commit is actually the parent of the other, shown by that red line between them. We took a commit and we modified it and created another commit, which is now the ancestor, the child of the original commit. And the information that makes it possible for Git to keep track of which commits are the parents and of which, or which commit should be the parent of the commit you're creating, is branches. And we'll look at branches in our next class. But for now, verify that you have another commit. If you use git log -- graph to print the commit graph, the commit DAG, you should see that you now have 2 nodes in the commit graph, 2 commits in the commit graph, and one of them corresponds to the one you just created. Now what I want you to do is to run git catfile -p on the new commit, and you can see that it has a new entry that the previous one didn't have, namely parent. This is a commit which has a parent commit. And the parent commit hash should be the hash of the first commit that we created. And that's what I wanted to show you today. How we create commits, the index's role in creating commits, and how commits form a graph. And if you take nothing away from this course except for a single fact, I want you to remember that the commit graph is the essential object, the essential Git data structure. It's what we care about when we use Git, the commit graph. And commits relate to each other through ancestry. Commits have parents, and the parents are basically the commits that we modified in order to get the new commit. What we did today was to first create an initial commit which did not have a parent. Then we modified the data in that commit and created another commit with the first commit as its parent. We got a very simple commit graph, basically 2 nodes and 1 edge. And tomorrow we'll look at what branches are in relation to the commit graph and how they work. So just give me a heads up when you're ready, and tell me if you were able to do this exercise. So very good. I'm going to give you a little bit of time to get ready. Now, you were given a problem set last time, and a lot of you have done some of it, but most of you are not done. You will not be given another problem set today. Instead, you'll be given time to finish the one that we gave last week. And please do finish it. Otherwise, the next classes will be very difficult. I think we've gone through everything you need in order to understand the current problem set now. We've talked about the object store and blobs and trees. We talked about garbage collection, and we've now covered commits as well. So that means we've actually covered most of the complexity of what Git is and does behind the scenes. Once we've covered branches, you've basically seen all the small objects and details that tie together into making Git work the way it does. And that's actually pretty exciting. And we'll see how we'll see how everything relates to the real life usage of Git once we get past the section on Git internals. But what I want you to take away from all this talk about Git internals is a model inside your head about what Git does. I want you to think about what the commit contains. I want you to remember the commit graph. I want you to remember that what you're in essence creating when you're using Git to keep track of your files is a commit graph that grows over time. And we'll see more about why it works this way, and what branches do, and what branches are, and what merging branches entails, and what rebasing is, and all these things that are basically just graph operations. If you remember, a little while ago I said that in essence GIT is just a graph manipulation tool that supports version control methodologies. And I think we'll see how true that is pretty soon. So anyway, thank you very much for following class today. We're a bit late. It's 1:15. We've gone on for almost a full hour now. I'm very sorry about that. Thank you very much for following the class today. I hope you'll be able to finish the problem set, and I look forward to seeing all of you again tomorrow. Have a good day.